looking at this slide, for me, the first, the key takeaway is that you can literally explore for deepwater or stratigraphic trap in various depositional and tectonic settings. You can see the spread right there. And so the reason why I have this up here is that the Niger Delta is probably no exception. The other thing that you can also see on the slide is that we have not really been exploring for purely deepwater stratigraphic traps in the Niger Delta. Now, as you can see, I think the task for all of us as explorers working in the Niger Delta basin is probably to flip the Niger Delta polygon green. I think in the near future. And then another key observation is that if you look at the polygons that are colored green, they basically highlight where the majors, the IOCs, are probably putting their money. I mean, if you put on your pre-COVID goggles, you will see that most of the polygons that are green are probably places where potential FIDs were about to be made before the global pandemic. But then some of those FIDs might have been delayed, but surely not suspended, right? And then, in addition, they also highlight, country opening discoveries that, driven largely by deepwater stratigraphic traps. A couple of the places that you see green are, places that, have, virtually no upstream offshore infrastructure. And then, of course, but then the size of the discovery is large enough, to drive a country opening venture. So clearly, this also shows the importance that deepwater stratigraphic traps will share in the portfolio of upstream companies in the coming decades. Okay. All right. So before I proceed, I think it's important for me to sort of define the type of deepwater stratigraphic trap that we are referring to, and then sort of characterize the essential components of this trap type. So the focus for this presentation here is on deepwater stratigraphic traps that are formed in the domain of unlimited accommodation in slope basins that are fully decoupled from shelf or shallow marine mechanisms, and is developed by essentially depositional autogenic processes. That is, processes that are internal to the depositional basin. As is shown on the stratigraphic cross section above. Deepwater stratigraphic traps are usually upper to lower slope embedded, sand-rich distributary fans, as we will see in the course of this presentation. In addition, if you look at the cross section, also, they have also been found to develop in deepwater conditions that are associated with steep delta front progradation, and those class of deepwater stratigraphic traps may be really vital or may be common in the Niger Delta. Now, one unique component of deepwater stratigraphic trap is the deep seal, or what we might essentially refer to as the depositional pinch out. This is one unique characteristics of these trap types. Other components might include a good base and lateral seal, and obviously a good top seal as well, as is shown on the chart to the top right. And then an example of the deepwater stratigraphic trap that I just described is also shown on the seismic extraction to the lower left, and that is the Barra discovery in the Sergipe Basin offshore Brazil. There are other kinds of configurations that can give you deepwater stratigraphic trap in slope basins. But the type of trap that we are looking at today are traps that like I mentioned, developed through purely autocyclic mechanism within the slope basin. Other trap configurations that you might have may include trap types that you have distributary channels and lobe complexes that is offset by an erosional channel, or you could have a channel fairway that is probably offset by an MTC. These are also deep water stratigraphic traps, but I'm not going to be focusing on them today because the whole aim for me is to sort of go over the type of traps that we can actually predict their formation mechanism. In other words, they form through some form of self-organizing mechanisms that we can predict, so that when we see them we can recognize them. That is the whole idea. The other trap types that are also some form of configuration of deep water stratigraphic traps, it's more of a coin flip. It's either the deep water deposit is offset by a channel, or it's not, or you have an MTC or you don't. And so you can't really predict that, because it will happen on case by case basis as you move from one basin to another. So there's really no predictability with that. So the whole purpose for me today is just to go over sort of the self-forming mechanism of these trap types, and so that when we see them we can recognize them, or when we see events that can lead to their formation in deep water basins, we can sort of focus our exploration concepts in that direction. So one thing that we did in the work that fed into this presentation is that we focused on key relevant variables that support the development of this trap type that I've just described. And then from a process stratigraphic, we used some form of process stratigraphic analysis. We looked at over 200 wells in the circumatlantic passive margin basins, and then we pulled information regarding these key variables and how they can correlate to success in deep water stratigraphic trap exploration. So in the course of this presentation, you will hear me sort of reference the database that sort of fed into some of the learnings that I'm presenting here. Now let's remind ourselves of the structural and stratigraphic components of the basin of interest. The stratigraphic interval of interest for exploration of deep water stratigraphic trap, for us covers the Miocene sequences of the Niger Delta basin. The dominant structural element in the Niger Delta includes extensional tectonics that is associated with high rates of sediment deposition. We have a Mobil shale related deformation, growth faulting, and the rest of them. The extensional tectonics are common in the proximal delta area, and then this basically transitions through a zone of translation to compressional deformation in the distal delta, as you can see in the image to the top right. Stratigraphically, the sediment field in the delta comprises three main lithostratigraphic formations that we are all familiar with, and we can see that on the stratigraphic chart. Sedimentation is highly progradational, and like I mentioned, we have both shallow, marine, and deep water deposits in the basin, and this is really important because at the frontal end of your prograding delta, most of the time we have mechanisms that can actually help us develop deep water stratigraphic trap deposits. So the reason why I brought this up is, just to highlight, just to show that, the high variability in sedimentation and structural styles that we have in the Niger Delta Basin can actually provide or support the necessary geologic variables for the development of deep water stratigraphic traps, as we will see later in the presentation. And some of the examples I will show will be drawn from the areas shown in the blue rectangle. So now let's try to understand deep water deposits from a process perspective, like I alluded to earlier. There are three main process mechanisms that influence all sediment gravity flow deposits, and they include the fluid mechanics, the sediment transport, the bed morphology, all these make up what we call, the morphodynamic character of every sediment gravity flow. In other words, all sediment gravity flow deposits are essentially a product of these three process mechanisms. Sometimes they are referred to as, the sedimentologic trinity. In other words, they all act in equal proportion on every sediment gravity flow deposit. But for the most part, when we visualize sediment gravity flows, we tend to focus on just one aspect of the flow, which is sediment transport. The flow hydraulics and its evolution through bed form development and interaction, is often overlooked. But it's also important for us to have a complete morphodynamic picture of the flow. It's important for us to focus on every aspect of the sediment gravity flow for us to really understand, get a full picture of the flow. The reason being that this will enable us to, sort of determine what type of flow can be linked to, what type of deposits by essentially analyzing the dominant bed forms that are associated with the flow, and of course their geometry and the facies distribution in the deposit that's a product of the flow. And basically, channelized sediment gravity flows interact differently with their deposit and of course the pre-existing bed morphology depending on the gradient of the flow. So gradient is really an important factor, and we will see that come up more often in this presentation. And this is important because flows on steep gradients, tend to exhibit different hydraulic states compared to flows on lower gradients. Now, while flows on steep gradients, will undergo what we refer to as a hydraulic jump upon encountering an obstacle. On the other hand, flows from on lower gradient would sort of exhibit what we refer to as the backwater effect, and the hydraulic jump and the backwater effect, whether you are looking at flows on steep gradient or lower gradient, these are hydraulic states that enable this type of flows to basically sort of dump their sediment load. So we can see that gradient exerts sort of a first order control on deep water deposits, their facies content, and of course their bed form characteristics as well. And some of those unique bed forms that are associated with different types of flow will include upstream migrating cyclic steps, anti-dunes, wavy beds, current repose. And then in the next slide, we will look at how we can describe the hydraulic state of sediment gravity flows and then make a link between the dominant flow type, the type of deep water deposit, and of course the genetic basin evolution, and how this will help us focus on which part of the basin field that we can be focusing for a stratigraphic trap exploration. So sediment gravity flows, like I mentioned, they are part of the flows that we describe as having an interface. In this case, the interface being the ambient fluid and surrounding the flow. The hydraulic state of any flow with an interface can be described with a dimensionless constant known as the densimetric Froude number. Now, the Froude number represents basically the ratio of inertia versus gravitational forces acting within the flow, and it's a function of the layer average current velocity, the gravitational acceleration, the vertical density stratification, and of course the height of the flow. And this is shown on the slide to the right. Now, when the inertial force within the flow exists is gravitational attraction, we have what we refer to as a supercritical flow. And then, of course, the densimetric Froude number is greater than 1 in this case. In the reverse case, we have a subcritical flow. So the primary implication of this for us is that in supercritical flows, internal perturbations of the flow only migrate downstream. In other words, they're basically forward-looking. On the other hand, subcritical flows, internal perturbations can migrate both upstream and downstream. So we can basically liken supercritical flow as a sort of a jet flow mechanism, through small conduits, and because they can't transmit information backward, and they are very efficient in the concentration of sands through bedload transport. And then based on some of the work that we've done in flume tank experiments, we found out that the supercritical flows are, basically associated with relatively high depositional gradient. They are associated with channels that are dominated by bedload transports that is being fed, or feeding small radius sandy fans. And this small radius sandy fan is sort of our key focus today for developing deepwater stratigraphic traps. Subcritical flows, on the other hand, are associated with, mainly lower depositional gradient, with mostly a gradient suspension deposits of both sands and shale in channels and levees that is feeding a much lower net fan system that is further out in the basin. And of course, I talked about the flow transformation mechanism, the hydraulic jump for supercritical flows on the previous slide. They are basically associated, with the supercritical flows, and they sort of, play a role in locally changing the hydraulic state upon interaction with pre-existing bed morphology or obstacles. And when this happens, the flow height locally increases, and this enables the flow to locally dump its sediment load through its narrow feeder conduit, while the suspended mud that is associated with as part of the sediment gravity flow is deposited further out in the basin, thereby generating sand deposits that could potentially develop into deepwater stratigraphic traps. And so, this process, as I mentioned earlier, is, sort of self-organizing. We'll see more of that in the course of the presentation. And then the other aspect to it is that, there is some form of predictability on how this process sort of leads to the generation of, sand-rich distributary channels and lobe complexes. And also, from the flume tank experiments, we also noticed that you can actually distinguish supercritical flow deposits from subcritical flow deposits by looking at the dominant, bed forms that is associated with these flow types. So now, let's look at some of the models that we developed in our work for predicting deepwater stratigraphic trap development, and how we tied that to the genetic basin evolution. And also, this is also results from this is was also fed from the 200 plus wells that we gathered information on from the Atlantic passive margin basin. So typically, following the creation of rift basins, as we see in passive margins, the passive post-kinematic sediment field genetically evolves from a high paleo-depositional gradient to a generally lower paleo-depositional gradient, as you can see on the stratigraphic model to the left. Now, on this model, we see how series of shelf sediment delivery timelines sort of map into the sediment receiving basin. Now, initial rift shoulders, sort of provide high depositional gradient, and at some point, your shelf sediment wedge sort of decouples itself from the basin bounding fault, and more sediments are then delivered into the receiving basin, essentially reducing the paleo depositional gradient at that point. So the implication of this is that you can have, like I mentioned before earlier on, you can have different deepwater flow hydraulic regimes that will be dominant at each phase of the basin passive field history, and that is basically the transformation from an early high gradient to a late low gradient phase. And so when that happens, you can have different types of submarine fans can be expected to develop at each phase within the basin evolution. And so you can see clearly on the slide, how you have, the different timelines, that sort of feed into the basin. And you have, dominantly, supercritical hydraulics that would, be more in operation in the earlier part of the basin field history. And of course you would deposit mostly sand rich distributary fans at that stage. And then as the overall depositional profile of the basin sort of evolves, the sediment pathways and fairways sort of organize themselves into well entrenched feeder systems, and then they feed a more muddier fan that is further out in the basin. And those fans are the fans that are associated mostly with subcritical flows, because most of the sediment gravity flows are flows that are mostly subcritical in their hydraulic nature. And then of course we documented different fan types. You can see that on the lower left on the slide. And for us, the key focus for deepwater stratigraphic trap exploration will be the sandy fans that are fed by very narrow channels. And if you look at some of the key geologic parameters that we gathered from fans of this type, especially the net to gross, their connectivity, and of course their stratigraphic trap potential, they are much higher compared to the other fan types that are associated with subcritical flows that you find further out in the basin. And then another thing that we did was to sort of check what is the failure rate, in these fan types. So we realized overall, at least in a gross scale, that if exploring for purely deepwater stratigraphic traps, you have a much lower failure rate associated, with the distributary channels and lobe complexes that are deposited, through supercritical flow hydraulics at the earlier part of the basin evolution. And then, of course, there are much higher number of failure rates associated with the much lower net fans that are associated with the subcritical fans that you find further out in the basin. And so, like I mentioned, these supercritical fans, they have the higher tendency to generate deepwater stratigraphic traps. And like I mentioned, because their sand feeder conduits, exhibit, almost a complete sediment bypass due to the nature of the flow. And of course, they can be easily shut off by other processes, thus leading to the development of deepwater stratigraphic traps. Another observation that we had in the circumatlantic passive margin, sort of ties to the model that I showed earlier. And this slide shows seismic evidence of sort of the two-stage post-kinematic sediment field for most of the passive margin deepwater environment. You can actually, clearly see this most, better on strike lines, and that's why I've put up two strike lines here from, different basins on opposite sides of the Atlantic passive margin basin. And then you can see, clearly on first observation, sort of the overall dominant architecture of deepwater deposit at each stage of the basin evolution. Initial deepwater deposits that you have at earlier stages in the basin evolution are dominantly distributary, and this basically transitions into more entrenched levee and erosionally confined channels that have dominant fairways, and of course, providing sort of that fundamental control of gradient on the depositional style and facies distribution. Now, this sort of a two-stage, field. Now, the interesting thing is that even on opposite sides of the Atlantic, you sort of see this two-stage field where you sort of progress from the earlier stages that is dominated by distributary channels that are fed by narrow feeder channels, compensationally stacked, and of course, not having well entrenched fairways. And then in the later part of the basin evolution, you have more organized fairway. The dominant variable here is basically gradient, and that's what's really at play here. So this distinct separation in EOD and architectural element for us was a proxy for estimating paleodepositional gradient variation across the passive margin basins. And of course, also tied to some of the experimental results that we had in the flume tank experiment. Now, not all the time that you would see sort of this two-staged, genetic evolution along the Atlantic passive margin. Now, there are other factors, other extrabasinal factors that can, sort of, change the switch of events. For instance, you could have transform faults that are active at the time of, the basin fill, and that can potentially change, sort of the order. And most times, you have basins where you don't really sort of repair the depositional profile in time to have the organized fairways. On the other hand, or another example, another cause is that you could also have bottom current deposits. Most of the times we focus on just sediment gravity flows, but out there you have, ocean bottom current deposits that could actually deliver plaster drifts that can also change the depositional profile, the overall depositional profile. And then of course you can have canyon systems that can actually sort of be a sediment sink, and in that way form sort of a point source into the basin. And of course, you will find out that the post-kinematic sediment fill may not really evolve, from that two-stage process where you go from much lower, much higher paleodepositional gradient to a much lower paleodepositional gradient. So for us, this is sort of insightful in that it basically gives us sort of a first principles approach to determine where to look for deepwater stratigraphic traps in any frontier basin. Okay. And then based on all we've discussed so far, we can essentially isolate, some key measurable geologic variables that can support deepwater stratigraphic trap plays. Like I've mentioned, there are, the high paleodepositional gradient at the time of deposition, the sandy fans that are fed by narrow channelized conduits, and of course, having a dominantly supercritical flow hydraulics that is internal to the depositional basin. And so this slide shows exceedance probability plot that compares total discovered volumes in channelized low gradient systems to discovered volumes in distributive high gradient systems. And the results shows that you have more potential to have more volumes, especially in the dominantly supercritical deposits, which are the sand-rich distributary channels and lobe complexes that are deposited in the higher paleodepositional gradient. So that's another sort of key business insight, that overall, if you explore for these types of systems, there is data out there that shows that you have more total volumes in place associated with play systems like this. The other thing I would like to, sort of go into is to look at the validation, for some of these concepts, and of course look at also, like I mentioned earlier, the predictable nature of, how the sand-rich distributary fans, sort of developed overall. Now on this slide, we show both experimental and field observation validations of the concepts that is that is being presented here. And these validations I will mention largely, draws from, work that is already that's already existing in the literature, as you can see on the slide, mostly work from Hoyle and Sheets, Postma and Cleveland, and of course the more recent work of Vendetuoli. And also, these observations are very much in line, with the observations that we've seen in the database that we generated in the process of our work. Now, the experimental validation basically shows results of a flume tank experiment that developed through various stages in high gradient for a sandy fan that is deposited under supercritical flow hydraulics. Now, these sandy fans, as you can see on the chart, they sort of develop through the stages that are listed from A to F on the slide. And the summary basically is that, on high depositional gradient, you have, sort of the flow hydraulics, the supercritical flow hydraulics, and of course you have, the hydraulic jump process all in play. Now, how does that all come together in sort of a predictable fashion? Well, initially, when the supercritical flow basically encounters an obstacle, and then it dumps its sediment load, what you have is basically an initial channel incision and extension, and of course, the deposition of the initial mouth bar lobes, and that then the flow basically interacts with the bed forms that are associated with the lobe deposition, leading to deposits within the feeder channels that is, depositing the initial mouth bar lobes. And what happens is that, the mouth bars interacts with the flow, and then of course you have, the hydraulic jump process, and then you have, subsequent up-dip avulsion. And so basically, like I've mentioned, you have the initial channel deposition, which mostly, channel progradation, and then of course mouth bar aggradation, interaction with the flow, and then of course up-dip avulsion or retrogradation. And then this three-stage process, is sort of seen as, a compensational stacking mechanism that you have in most distributary channel and lobe complexes. So, and observations of, the various high gradient sand-rich distributary channels and lobe complexes, basically show this three-stage process. And this process is, referred to as the avulsion cycle process. And of course, most sandy fans in the deepwater environment that have, the potential for deepwater stratigraphic trapping, sort of evolve through this process. And then, of course, you also have, the model to the top right that is from an outcrop study that basically shows that, through observation on outcrop, you can have this three-stage process of avulsion cycle. And what really happens is that most of the supercritical flow hydraulics are, type of flows that that are referred to as decoupled flow. So basically, when they dump their sediment load, mostly bed load, coarse grain sands that are part of the bed load, the mud associated with that particular flow in time is deposited further out in the basin. So basically, the flow sort of has this ability to concentrate, sand-rich deposits. And then, of course, you have, for being in the slope environment, then you have the potential, for the narrow feeder conduits that deposit this sand to be eventually sealed, by, later mud system, thus giving rise to deepwater stratigraphic traps. And then also looking at, the high resolution bathymetric image that we have to the bottom right. You can also see, that, so this is an image that is, was acquired from the Squamish River Delta in BC. And basically shows that the is sort of an evidence that the supercritical flow hydraulics can actually result in net sediment bypass along the narrow conduits that feed the lobe system. And so you can see, so this chart shows, you can look at the scale here that shows where you have net deposition versus net erosion. And you can see within the feeder conduit for systems that are deposited by supercritical flow hydraulics, you can actually have net sediment bypass. And then, of course, later on, you have the potential for sealing of these narrow conduits with slope mods, thereby generating a deepwater stratigraphic trap. And one way to recognize that this is supercritical, or this deposit was deposited by supercritical flow, is the dominant bed forms that we find within the channel feeders, which are very distinctive bed forms that are associated with supercritical flows. Some of them being the upstream migrating cyclic steps, and I'll have a slide that shows that in more detail in the coming presentation. And so the next slide basically shows the avulsion cycle process in more detail, as I've mentioned earlier. So this is a high resolution bathymetric image that clearly shows that predictable order in the development of sandy fans with potential for stratigraphic trap development through supercritical flow deposits. So within the feeder systems, we have unique bed forms that sort of very distinctive for deposits that are associated with supercritical flow. So those bed forms are what led us to make the call that what you have here is dominantly supercritical flow hydraulics. And so on this chart, the panels on the top is basically the same as the panels that you have to the on the bottom, except that we've applied some filtering, and this is a work that is done by a research consortium that is led by Hughes Clark that we work with. And of course, if you look at this, some filtering has been applied to the lower panel just so that you can see, the internal architecture of, the lobe system that is, on a modern environment. So the initial part of the avulsion cycle process that I described, you can see that clearly. The areas where you have, dark colors are areas of net bypass. And then, of course, areas where you have, white colors are where you have, net deposition. And so you can see clearly as the three-stage process that I described earlier, channel incision and progradation, and of course the flow, the mouth bar deposit then interacts with the flow, and then you have up deep backstepping, and then you have a up deep avulsion, and of course the process continues again. And you can see that clearly. This is a continuous monitoring data that spans from 2004 to 2017. You can see clearly how this lobe system sort of developed through avulsion cycle process. And the insightful thing is that the fact that most of the time flows that are associated with the supercritical hydraulics tend to create that net sediment bypass within their feeder conduit, and that's what is really key for the development of deepwater stratigraphic traps. And when we see deposits that are associated with this type of flow, what we are really looking out for is this avulsion cycle mechanisms. Do I see the predictable avulsion cycle process? And of course, can I make a prediction that this deposit was probably deposited within a high paleo-depositional gradient at the time of deposition? And so basically looking out for the key variables that can help make that call. And then of course, integrating other geologic evaluation tools to sort of reduce the uncertainty associated, with that particular prospect. Okay, so now we're going to move on to looking at some examples in the Niger Delta that might, sort of, be the result of supercritical flow hydraulics, and of course having a great potential for deepwater stratigraphic trap development. So we've looked at different geologic settings that could set the stage for supercritical flow hydraulics for the development of deepwater stratigraphic traps. We've seen what really matters for the development of deepwater stratigraphic trap from a process perspective. And so in application for searching for these trap types in the Niger Delta, what we need to do is basically to explore for the geologic events that can create a local accommodation in the slope environment, and then evaluate the sediment field, especially in the early stage where you would have the early high gradient stage. And of course, this might be the area where you can search for deepwater stratigraphic traps. And of course, within the Niger Delta Basin, we know that we have a couple of sub-basins, and some of those sub-basins are set up by key tectonic events. And so those are areas that we might sort of focus our attention for these short radius sandy fans that are fed by narrow conduits that have the high potential for stratigraphic trap development. And one of such events in the Niger Delta is the gravity-driven down to basin faults that create huge accommodation, thus setting the stage for possible supercritical flow hydraulics. On the slide, we see a typical short radius sandy fan that was deposited in the early phase of passive fuel sedimentation in a local accommodation that was created by a regional down to basin fault. And then, of course, based on our analysis, we see that there's the possibility that we can identify similar plays like these within various sub-basins in the Niger Delta, and possibly across various age stages as well, because we all know that these fault systems that create huge accommodation, they are very common in the Delta. And also sometimes the fault system can create pre-existing topography, pre-existing complex topography that could also create local high gradient high gradient locations where supercritical flow hydraulics can actually sort of nucleate and lead to the generation of sandy fans. Then the other one that we have is the local accommodation and sediment routing that are created by Mobil shale tectonics, and this is also common in the Niger Delta. These structural features, basically, they create the depositional reliefs and the local accommodation that could potentially set the stage, for supercritical flow hydraulics. And this example here, we see how growth in the Mobil shales, as shown on the map, can actually set up, the high depositional gradient necessary for the deposition of sandy fans that have a potential for a deepwater stratigraphic trap development. The last example I will show is also common in the Delta, and that is basically a shelf collapse event due to high rates of sediment deposition. This process, as we all know, they create deep water accommodation in a couple of places. They create these accommodations instantaneously. And of course, the the local sub-basin, that sort of evolves from that, we get filled by initial high gradient deep water deposits. As as is shown on this seismic line, in this example, you can actually see the escarpment created by the shelf collapse event. And then, of course, you can see the initial sandy fans that are deposited, within, this local accommodation, possibly through supercritical flow hydraulics. And of course, they also exhibit, up-deep sediment bypass. And so this event is, based on our analysis, is, quite common in the Delta, and of course, distributed in a couple of location, and of course across multiple time intervals as well. And of course, we all know that in the Delta we have high rates of sediment deposition. And of course, multiple collapse events do happen in the Delta, and so this would be areas that might be, might be, the key focus areas, to explore for deepwater stratigraphic traps. So the question now is, how can we evaluate the seal risk associated with this trap type in a typical exploration scenario? And based on the analysis we did with our database, what we observed, is basically, a continuum, right? But then, we sort of singled out, three, common up-deep reservoir geometry that can help us, sort of evaluate the seal risks associated with a deepwater stratigraphic trap deposit. First of all, we want to make the interpretation that the sandy fan probably has a compensational stacking due to the avulsion cycle process that I talked about, and that the fan is, basically decoupled, from shelf processes and deposited, probably in the early passive field of your local accommodation. Of course, then that would increase, your confidence of a potential, robust deep seal. And of course, you also have to evaluate, the other stratigraphic component of the trap, the base seal, the lateral seal, and the top seal as well. The highest risk, they are basically associated with the deep water reservoirs that are deposited, very close to the shelf, and of course, maybe within fairways of an established long-lived channel feeder system, with no evidence of avulsion cycle process that you can actually see in the stacking of the reservoir. And so you don't really, you cannot make that predictable interpretation that, what you're looking at is probably deposited through the avulsion cycle process. And of course, you can map, the feeder system all the way up to the shelf. And so the challenge is, how do you shut off the sand supply, to the deposit? In other words, whatever charge you have within that reservoir from a purely stratigraphic trap perspective will probably leak out. And so you're looking out for systems that are deposited, by supercritical processes that are fed by, very narrow channelized conduits that have the potential to develop deep seal. Also, evidence of, like I mentioned, evidence of compensational stacking, that shows that initial progradation of the first lobe complex followed by the retrogradation and subsequent avulsion, that sort of gives you that interpretation of an avulsion cycle process, gives us a higher confidence versus, lobe complexes that are dominantly aggradational across multiple intervals, where you don't see that potential avulsion cycle mechanism, being, sort of shown in the deposits. And then, of course, you can, have out of these three up-deep reservoir geometry that we have, you can have, variations of them. And then, of course, you can then apply other geologic evaluations to narrow, your uncertainty. So, in conclusion, we looked at how industry interests in deepwater stratigraphic traps have evolved over time. And based on recent results or recent exploration results and analysis from a vendor data, you can see that these play types are not necessarily as risky as maybe perceived. We also saw that the potential large finds of the future, maybe deepwater stratigraphic traps, as the easier and more obvious play types are drilled out. Then we looked at the process stratigraphy mechanisms that could help us understand the geologic variables necessary for the development of deepwater stratigraphic traps. And then, of course, based on this process stratigraphic knowledge, we looked at the results from our database that basically inferred that short radius sandy fans deposited in high paleo gradients under supercritical flow hydraulics have the higher potential to actually lead to deposits, with higher volumes in place. And so those are the type of deposits that are of economic value, for a deepwater stratigraphic trap exploration. And then, of course, we looked at some key events in the Niger Delta that could support deepwater stratigraphic trap development. Okay, so that is all I have, and I would like to sort of extend my appreciation to ExxonMobil and of course NMPC for permission to deliver this technical presentation, and also acknowledge contributions of the ExxonMobil research company and thematic studies, and of course to NAPE for providing the platform through this virtual technical webinar to share our ideas. And then also all the recognize all the authors whose work are sort of cited here, and of course vendor studies reference in this work. And finally, to everyone for participating. Thank you very much, and I will take your questions now.
Thank you very much, Francis. That's very good, very insightful. It's been a wonderful presentation, and it's pretty, most of us, for most followers, explorationists that are listening in here, this is the bread and butter of what exploration is all about. Thank you for really bringing it to light. Just as a summary, I'll just mention a few things that will be a pointer before we start. I will turn it over to our moderator, and then we'll start taking some questions and some comments from the people who are listening in. One of the things, he started off by making some sort of provocative statement. He said, more oil and gas was discovered in clastic strata in the last decade. And that's what he's trying to assert, that we have more oil and gas than we think was discovered in clastic stratigraphic traps in the last decade. And he said stratigraphic traps are not as risky as we perceive. And that's really the essence of the presentation he was going into. So he observed that the running room for huge discoveries in conventional strat traps is diminishing. And he showed us basins with significant traps that are stratigraphic traps discoveries since 2008. He explained that where we find deep water traps, exploration opportunities, he showed us some of the, that is the data from 200 deep water stratigraphic deposits from second Atlantic margins. And he used this to explain most of the things he was, the data that he garnered from these areas to explain some of the things and the mechanisms which he demonstrated. We understood from his presentation again that deep water flow processes, he talked about the fluid mechanics, he talked about the sediment transport, that's the flow dynamics. He talked about bed morphology. He then went into details to talk about supercritical flow versus subcritical flow hydraulics, and looked at some of how these interrelate with the gravitational force, of course, which provides the definition of what they are. And then he looked at how supercritical flow sort of in an object shows in the distributary channel complexes, how it plays a part in it, whether in the confined case or amalgamated case, and where the subcritical flows multiple. In most cases, you have these in the down in the distributed fan lobes that are further down to the basin. He was very, very he gave me a very good insight into really some of the observations that I have made not only during my own practice, but also in the consulting business, which I have looked at some of the data that is from other companies. One of the things he pointed out again during this discussion is he looked at today's study, somehow how we should look at paleobasin analysis and study these critically in such a way because they point to what type of hydraulics and attendant depot form that we should be expecting. He tried to illustrate that by looking at tank model experiments and how these validate the actual field observations. In fact, he brought us home to what we have in the Niger Delta. And he explained the interplay between the growth regional fault that we have that create accommodation space. And these ones could set up some stage for the supercritical flows, which are really the things that give us the kind of depositional environments he's looking at, he explained. He also touched on shelf collapse that also creates some similar such space accommodations that trigger off some supercritical flows. But one of the key things he looked after looking at these two observations, he admitted towards the end that still one of those things that concerns us, that worries us, that becomes some bit of concern in the industry is actually the seal component of stratigraphic deposits. This is what has always been the challenge. What seals and what doesn't seal. But one good thing is that when we encounter and query the data and look at, do we have some progradational and retrogradational aspect of it and avulsions, then when we see this interplay, it begins to increase our confidence in the seal nature of the deposition that has taken place. So he concludes by saying that understanding the process mechanisms and recognition of the criteria for different types of the distributary deep water deposits will further enhance significant discoveries in the Niger Delta. Because what is happening is that we are running out of those big discoveries, both the ones that are defined by a structural setting, and even some that we have discovered so far in some of the areas that we are very conversant with in the stratigraphic traps like the BQI and the rest of it. But we need to be looking out further down the basin, and this becomes very critical at this time when there is going to be the next cycle of bidding that is going to come up, hopefully after maybe next year, early next year, after the PIB has been passed, so that we have both the physical and commercial incentives to go out in search of these deposit stratigraphic traps in the deep water setting of Niger Delta. And with that, I think I will hand over to the moderator so that we can have some questions or comments, because most of us have listened to this presentation and some of us are also involved in this quest to really, where do we find the next big discovery within the Niger Delta? Thank you very much. Francis?
Okay. Again, good day, everybody.
Thank you,
Thank you very much. Thank you very much, Mr. Chairman. Clearly, your bio is inaccurate. They say you've retired. I don't think you have. But back to the session of the day, we have a question from Godwin Sokowonchi Lakube. What makes up stratigraphic trap? What make up stratigraphic trap more suitable traps than other types of Niger Delta traps? So I think it's just trying to say what makes stratigraphic traps more suitable as a trap as compared to other traps in the Niger Delta. That's that question from Godwin. You want to take that right away, Francis?
Yes, I will take that. I will make notes as well. So, like I said, stratigraphic traps, they are quite subtle. One thing we've seen, especially globally, is sort of, the volumes associated with these trap types. Now, in the Niger Delta, we've, focused on, sort of what I will call the low-hanging fruits, the ones that we are, sort of familiar with. Mr. Chairman has, enumerated some of them. And I think we are running out of space for those. And I think the key incentive, like I tried to demonstrate, is, the volumes associated, with these trap types. And of course, I also showed the key reservoir parameters associated with them, probably net to gross, reservoir connectivity. There are very good quality, reservoirs, and of course, in terms of, producibility, of course, you would actually have, much better EUR from this type of trap types that we are looking at. Basically the sand-rich distributary channels and lobe complexes that are deposited through supercritical flow mechanisms. So that's the key incentive. That, for me, that's what makes it, probably different, from other trap types that we've seen, for the most part within the Niger Delta basin.
Okay, thank you. We have
I hope that addresses the question.
It characterizes the differences between stratigraphic traps and other trap types. And I guess you also highlighted the commercial reasons why we should go after those traps. So I think that's adequate. So Kenneth Obeta from Chevron, he says, great presentation. Please clarify when said that more hydrocarbon has been found in stratigraphic traps. Do you mean stratigraphic traps in combination with structural elements, or entirely stratigraphic traps without any form of conformance with structure? I think that would be a question you probably want to take right away.
Okay, yeah. Yes, yeah. Yeah, let me take that right away. I sort of, saw that coming. Yeah, I think the reference is to purely deepwater stratigraphic traps that are deposited, in slope basins that have, complete run up deep, that doesn't have any form of structural support. So the typical stratigraphic trap that I showed earlier in the first couple of slides, those are the type of stratigraphic traps, that I reference for the most part. And they are the common stratigraphic traps that, following the play opening discoveries that we had in the Tano Basin and the Sergipe Basin, a lot of explorers went out, to look for, quote and unquote, similar look-alike kind of traps.
Okay. Okay. So,
and of course, as they drill through, knowledge of these trap types sort of increased. So thanks.
All right. So I think this lays the appropriate groundwork for the next question. So on slide 4, I noticed an anomalously high trap level near Ghana at 35. Any idea or for explanations on this jump in stratigraphic trap? So this is coming from Oyewole Fortune, University of Lagos. Did you get that?
Yeah, so I get that. Most of the traps that you have sort of focus around the Tano Basin, and of course, the other adjoining basins around it. And this is, basically the number is based on multiple tests, not just the key trap types that we've heard of in the literature, but tests across multiple intervals that can be individual traps in their own right. So that's where the number is coming from. And of course, in other localities, there are other areas, for instance, the North Sea, that you have, a high number that is associated with the polygons as well, for the same reason.
Okay. Gideon Giwa, excellent look at the factors critical for reservoir development. In your opinion, how critical are structural, charge, and trapping mechanisms in effectively chasing stratigraphic traps in the Miocene of the Nile Delta?
So I believe Gideon is talking about, basically two different things. Probably if I get you right, you are asking what role do structures play in developing deepwater stratigraphic traps? That's an important question. And I think most of the examples that I showed in the Niger Delta basically alludes to the fact that, for you to have that real estate, real estate in your deepwater domain, basically you need some form of, structural event. But the deposits in themselves, at the end of the day, are basically decoupled, from processes associated with that, with those structures, and they basically develop through autogenic processes within that accommodation. Those are the trap types that is the focus of this presentation.
Okay.
Did you get that?
Yes. Thank you very much. We have Noye Afolabi. Our question is pretty simple. Please, could you give more details on the characteristics of this stratigraphic trap on seismic? And I think you should couple that with the question from Daniel Michelia. Can you please explain the relationship between supercritical flow and avulsion with respect to up-dip sill formation? All right.
Okay, so I will take the first one. So basically on seismic, what you ought to be looking out for, especially if your seismic has the necessary bandwidth or resolution content for you to see sort of the individual components of your distributary channel and lobe complexes. So you want to be using, probably seismic facies analysis, and of course, analysis of the geometric elements of the deposit. Like I mentioned, you want to be looking out for lobe complexes that are deposited on a common depositional profile or a common depositional surface that basically alludes to the avulsion cycle process. The sketches I showed towards the end sort of shows basically what you might be looking out for from a geometric perspective. And then, of course, you want to be looking out for sort of the feeder system to that lobe deposit. How can you characterize the feeder system in a strike sense? Do I have more of a relatively smaller scale channels feeding this system? Those are the kind of things you want to be looking out for on seismic for this type of traps. On the other question, to talk about the supercritical mechanism that lead to these trap types. Like I mentioned, gradient is an important control, and if you look at sort of where I define the hydraulics of this system, you would see that the layer average current velocity is very important. And so basically, most of these type of deposits are associated with high gradient. And of course, that sets the stage for the supercritical flow to take place, to sort of nucleate and evolve, and then of course deposit its sediment load in the first place. And then of course, the sediment load is usually deposited following the interaction of the flow with pre-existing bed form or any form of obstacle, which leads to the hydraulic jump event that basically increases the height of the currents, and then the flow basically sort of evolves locally to a subcritical hydraulic and dumps its sediment load, and of course while the rest of the flow continues further down into the basin. And so that process is sort of a mechanism that sort of increases the possibility of depositing good quality sand within the distributary channels and lobe complex.
All right. So most of the questions we've taken so far has been on Zoom. We have a couple of questions from Facebook. So we have Araga Adeleke Aisha. Our question is first, she says very interesting presentation, and she would like to know, do you have any examples where avulsion relates to submarine fan and turbidites? And I'm sure she'll probably be very interested if you have any in Nigeria. And I think we should couple that with Shola Omotoye. He wants to know, could you please comment on lateral seals with respect to stratigraphic traps? And his second question, apart from top seal that you mentioned, could you comment on lateral seal? Okay, it's the same question typed twice. All right, let's have you take those two questions. One from Shola, one from Maraga Adeleke Aisha.
Okay, so for submarine fans, and I believe probably the first question is related to terminal submarine fans. Mm-hmm. Terminal submarine fans basically are fed by well-established deepwater fairway system, and so most of the avulsions that you see basically happen at the terminal fan itself. And the type of avulsion associated with those kind of system are different from the up deep avulsion that is probably that is associated with the supercritical flow deposits. Those avulsion basically relates to a complete fairway being shut off, and then another fairway continues depositing and continues feeding the submarine fan. And systems like this are dominantly subcritical, and they are generally low net overall on a gross fan scale compared to the deposits from the supercritical flow hydraulics. The second question, in terms of a lateral seal, for the most part, most deepwater stratigraphic traps that that I've seen, tend to have a well-defined lateral seal. The only challenge is that if you have maybe a late stage channel or something, or another fairway to the side that could breach that lateral seal. But the ones that form mostly on passive margins where you have complete run up deep without any other structural feature around it, tend to develop very good lateral seal due to number one, sort of the facies gradation that you have to the side of that deposit. The main challenge for deepwater stratigraphic traps, like I mentioned, is the deep seal. Once you can, sort of have, a well-informed prediction that you have, a robust deep seal, then you can begin to increase your confidence on that prospect.
All right. So we have, we're back to Zoom. We have Kehinde Olafiyoye. Again, very superlative insight from you. His question is, in terms of overall sand shale distribution within the deepwater stratigraphy, what class, 1, 2, or 3, does the Niger Delta deepwater sub-environment belong? As this has implication for first pass stratigraphic trap and reservoir risking. Then Precious Osho says, as we know, the deepwater is predominantly made up of shale, and now we are searching for sands within these shales. Does their thickness of the stratigraphic trap and even their volumetric validate business estimates? So those are two questions, one from Mr. Kehinde and the other Olafiyoye, and then the other from Mr. Precious Osho.
Okay. Yeah, I'll take the first question. The first question is a very good question. It's probably related to sediment caliber, in my opinion, sort of sand shale mixture that you have in systems like this. The Niger Delta is a very prolific basin. We've seen that, it's a super basin, good rock quality. Whatever trap type, and this is where I can generalize, for the most part, whatever trap type that you have within the Niger Delta, usually comes up with, very classical reservoir quality. Just going by the fact that you have, a basin that have a long mature history of sediment provenance. And whatever sediment type that you have, at least within the Miocene sequence, would eventually give you very good rock property at the end of the day, or very good reservoir property. Usually you have unconsolidated sediments, you have the whole range of your grain size, going from coarse grain through medium grain, and of course to fine grain. And of course, all that play a part in the petrophysical property of your deposit at the end of the day. So very good question. I think just to answer it in a short way, the class of sediment that you would have, basically cuts across all the trap types. So if you have, the usual trap types that we have in the Niger Delta, and of course the deepwater stratigraphic trap types that I just mentioned. The only thing also is that the supercritical flow hydraulics adds to a further sort of increase in sand quality, because most of the time you deposit coarse grain sediment, you deposit sand in preference to mud under supercritical flow hydraulics. So that would also give you relatively better reservoir quality. The other question is quite intuitive. The slope environment is probably, I would say maybe 90% mud, right? And then of course now we are looking for reservoirs within this slope environment. That is quite insightful, because sometimes most of the time we see people exploring for deep water stratigraphic traps, and they're still sort of focusing on sort of identifying the reservoir. It's quite easy for us to find the reservoir. For instance, if you have a distributary channel and lobe complex within a slope environment that I just described, that is probably 80 or 90% mud, that reservoir would definitely stand out for sure. So the key thing here is understanding what are the events that could be a pointer, where to look for. Like I mentioned, sort of the if you have an accommodation, where to look for in terms of the initial passive fill of that accommodation that you just created, is probably where to look for. And so if you apply those methodologies, you can actually narrow down on key places to identify key prospects.
All right, thanks, Francis. So next we have Chuka Chize. How do you guarantee charging if the preferred stratigraphic trap types are devoid of structural faulting?
Okay, thanks, Chuka, for that. So, like I mentioned, and it's a very good question. I talked about that. You need a good dip seal, you need a good base seal, and I guess the question is, how do you charge it, right? So the charging, for the most part, it's a combination of both vertical and lateral migration through sediment pathways that will basically charge your distributary channel and lobe complexes from their terminal ends. The other way you could charge it is to have probably seismic faults, especially where you have, for instance, in the Tano Basin, where you have the half grabons, where you have the initial source deposits, rich source deposit within the half grabons that develop during rifting. If you have what we probably sort of refer to as face loading, in other words, the prospect is directly sort of above those half grabon, and potentially if you have subseismic micro faults, that could just charge vertically. But for the most part, the charging mechanism that we've seen from a hydrocarbon systems perspective, is associated with source that is further out into the basin, and then migrates through a combination of both vertical and lateral migration to get into the trap. And sometimes you could have, systems that might be in the shadow of this migration pathway.
Okay. Are you still there? Can you hear me?
Yes, I can hear you.
Right. So we have a question from Emmanuel Adewale. What is the seismic attribute shown on the seismic section that clearly shows the progression of the sediments? So he's asking for features you see in cross sections that indicates that you have deposition that is prograding, essentially.
Well, if you have good quality seismic, you will look at your, sort of the stack of your lobe complex. Within the hierarchy, you should be able to map out sort of the initial fan progression, right? That is further out in the basin. Age-wise, you want to see that initial, frontal lobe system that sort of bevels out the pre-existing topography within your accommodation. And then you want to see, subsequent lobe complexes that, show some form of backstepping, and maybe to the side, you could have others that also, prograde due to up-dip avulsion as well. Those are the things you want to look out for on seismic. So mapping your deep water deposit from a hierarchical sense, understanding the hierarchy of the deposit and being able to interpret, which one prograded out into the basin first. And then, of course, you can that to me is a clear indication of how you can identify progradation within the deposit.
All right. So I got so two more questions, and I think we'll call it a wrap. So from your perspective, what do you think are the key extrabasinal factors that influence depositional profile, these stratigraphic traps and reservoir architecture? So the key extrabasinal factors that you think influence, number one, depositional profile, reservoir architecture, and overall these stratigraphic traps. Then the second question will be, so you've been able to gather a lot of statistics around passive margins across the Atlantic, all around the perimeter of the Atlantic. Statistically, what percentage of stratigraphic traps do you think have been identified in the Niger Delta? So it gives like a rough feel. We know it's statistic, but it gives a rough feel of what is yet unexplored and makes a lot of people, investors, excited. So for instance, the chairman was talking about hopefully if everything aligns, the PIB is signed, and the next bid round comes open, information like this will be very exciting to interested investors.
Okay, I'll take the first one. Hinterland processes and extrabasinal factors are important in a gross scale. They usually, like I mentioned, the stratigraphic traps that we are looking at, sort of are decoupled and from extrabasinal factors. They develop through autocyclic processes within the depositional basin. But overall, on a fan scale, on a gross basin scale, there are certain key extrabasinal factors that could also play a role. For instance, you could have, hinterland stream capture that could actually change the dynamics of sediment delivery within your basin. This actually happened in the Sergipe Basin in masturation time that basically increased the sediment load into that basin. It's one of the basins in the South America margin. And of course, it sort of delivered good quality mud within the basin. In other words, you have a system that has a long residence time in terms of the maturity of the sediments that you deliver into the basin. And one thing that we notice is that having good quality mud in that interval overall increase the stratigraphic trap potential for that particular stage interval. So that's one example of where hinterland processes or extrabasinal processes can actually play a role in helping develop deepwater stratigraphic traps within the depositional basin. Now, in terms of the Niger Delta, and of course, statistically, how much should we expect, for these trap types? One thing I would say is that if you look at a typical creaming curve for the Niger Delta, obviously, from most, one thing you would notice is that that's probably not creamed. So there are still play systems that are out there, and of course, deep water stratigraphic traps will be one of them. And of course, going through multiple age intervals, you can have this type of systems. And so my opinion is that I'm going to answer this quantitative answer to that. But in my opinion, there a lot of different mechanisms within the Niger Delta that can create sort of a, high depositional profile. We've not even looked at, the events that are probably associated, with the tow thrust part of the delta, and of course we still have sediments making it out there. And so there's also the possibility, that you could have, events that could sort of steepen your depositional profile and sort of lead you, or
down the
sort of,
basin.
create the environment for this type of deposit. So qualitatively, there's probably a lot out there. Probably what we need is, good quality data to image things properly and to be able to ID this type of trap systems.
Yeah. All right. Thank you very, very much, Francis. Good to try to get the president to join us. And before we take the sponsor's remark.
Okay, good afternoon again, Mr. Chairman, the President NAPE, President-elect NAPE, panelists, NAPE members, and all participants today. It's a great honor and pleasure on my part to acknowledge your inviting us and our acceptance of today's event to sponsor it. ExxonMobil over the years, over the decades rather, has had a long-standing relationship and association with NAPE, including sponsorship of several events, one of which is today's technical session. Our support of NAPE has also included supporting our staff to be actively involved in several NAPE activities, the annual international conference, community participation in committees, and like I said, also today's technical session. I want to specifically thank Mr. Chairman, Mr. Chikwe Dozim, for overseeing today's occasion, and my senior at, I recall, Mr. Chairman, in your opening remarks, you talked about a university, but I believe you were mindful of time and didn't want to talk about the university. So let me thank my president, my former senior in at the university, Mr. Alex Taka. I also want to thank the president. To thank and make also specific mention of ExxonMobil management, particularly Mr. Andrew Ezeh, who supports active encouragement, enabled the approval and support of this event, or sponsorship of today's event. I also want to thank Mr. Michael Udo as well, who was actively supportive of today's events. Finally, I want everyone to have taken the time out to come and share today. It's to give that in one sense of
So I think we may have some data-related issues. I don't know what's going on. Mr. Victor, are you still there?
Yes, I am. Can you hear me? Or did you hear me?
Now we can. So now we can. There was was intermittent. I think the last, you know. Well,
sorry about that. Okay. Okay, sorry about that. I'll just try to recap again briefly. Again, like I want to thank Mr. Chairman for today's event, for overseeing the activities that we have been through in the past 1 to 2 hours now. The entire NAPE Exco, in the presence of Mr. President Alex Taka, the President-elect Mrs. Patricia Ochogbu, Mr. Abdul Latif today for helping us moderate today's event, and all the other people who behind the scenes have seen to it that we have had a flawless execution and event today. I also want to thank specifically management of ExxonMobil in the presence of Mr. Andrew Ezeh, the General Manager Exploration, and also Mr. Michael Udo, the General Manager Geoscience in ExxonMobil, for the active support and that allowed for us to be sponsors today. And finally, I want to thank everybody, all the participants, for your active participation. Thanks for your questions, for your technical exchange that we have had today. It is my hope and belief that it has been mutually beneficial. We have gained as much as we have also been able to share in today's technical session. Thank you very much.
All right, over to you, Mr. President. Okay,
hello.
We can hear you now. Yes, we can
hear me. Can you see me?
Absolutely, sir.
Okay. On behalf of the NAPE Executive Committee and the entire membership, I want to sincerely appreciate, first and foremost, ExxonMobil, the sponsor of today's event, approval of this wonderful presentation with the JV partners. I want to appreciate the speaker for today. We thought even with the approval, we wouldn't have had anybody to listen to. We're in a trying period. We're excited about today's event because it's a lecture we're very expectant to hear about March, just before the lockdown. In fact, on the eve of the lockdown, we're happy that we didn't need to ship this into the new year, in spite of all the challenges. We appreciate the chairman of today's event, our distinguished president and a distinguished fellow of this body, Ezeh. So we appreciate you made time to be here. We appreciate Victor Bremer for that wonderful speech. Francis, we are so excited. This is a topic that looks complex. You have been able to simplify it and ability to take so many questions. We appreciate you. It shows the depth of how you understand this topic. We want to let you know that in the midst of challenges, just like DPR director said sometimes in July, if NAPE was to be a bird, NAPE would have been an eagle, ability to weather the storm. We've been globally linked. Francis, it will please you to know that about 350 participants were listening to you worldwide. We had people from the US, we had members from Europe and other parts of the world. That is what we've been able to achieve in the midst of lockdown, having our members at different global locations listening to very sensitive topics of this nature. About 350 participants were listening to you today. We wouldn't have been able to achieve that at Eco Hotel, I will assure you. We're excited about this feat, and we promise to sustain it into November during our conference. We appreciate every participant that have made time today to be a part of the success story of today. Without your participation, we wouldn't have been able to run this technical session. We are happy that in the midst of challenges, NAPE has been consistent with programs since the lockdown. And we hope to do this up to the virtual conference that we showcase in November to let others learn from us. We'll be expecting all of you to join us. Once again, we thank the publicity team headed by the Public Secretary, working closely with our distinguished PE, a distinguished fellow of this association, a very key management staff of ExxonMobil, where his constituency is. Madam, we appreciate you. We appreciate Public Secretary with the team. and most especially our staff, indefatigable staff of NAPE Secretariat. They are always behind the scene, working to make sure these programs run without hitches. We appreciate your contributions and we cherish each and every one of you. Finally, I want to announce to us that we sustain our programs. We appreciate every participant. Without your attendance, without your participation, this program wouldn't have been successful. We thank each and every one. Areas we didn't get up to your expectation, please bear with us. We're in a new normal. We continue to try our best, and we promise you that NAPE will not fail you under this leadership. Every executive member that have taken time to join, we appreciate you. Thank you, and thank you. Time will not permit me to continue making speeches. We highly appreciate. And we want to encourage you to continue to attend our programs. We're on every platform. So join whichever is convenient to you. Thank you once again. Have a wonderful day and a memorable week ahead.